Recall that our model for exponential growth is going to be this. A times 1 plus r raised to the t. A represents my initial amount, how much I start with. The 1 is in there because we're always starting at 100% and then either adding or subtracting depending on if we have an increase or decrease problem. R represents our growth rate or our decrease rate as a decimal always, and then t represents time. So let's go ahead and take a look at this example and get some numbers plugged in there into our model. And go from there. So we're starting with a zombie infestation, always a good way to represent exponential growth. And it says the zombie infestation began with a single zombie. So there's some important information that tells me my initial value, the A, is going to be 1 in this case. And then doubled each day. Well, doubling means a 100% increase. So my R is 100%, but remember that always has to be expressed as a decimal. So divide that number by 100 to get the decimal, so that's actually going to be just 1 when I divide that by 100, or move your decimal over 2 spaces. Growing exponentially, blah, blah, blah. How many zombies were there after 5 days? So there's the time that I'm dealing with first. Okay, so let's go ahead and get all that plugged into this model and see what happens. So our A value, our initial amount, is 1. In parentheses, I have 1. That 1's always there, plus the rate, which is 1. So there's lots of 1's in this example. Make sure you know which one is which, I suppose. And then I'm raising that to the 5th power to represent the 5 days. Okay? If I want to do a little bit of simplifying, even though it's not necessary, because I'm just going to type this to my calculator, I can write this as 1 times 2 to the 5th power. Now for all these problems, I would recommend you just type them in your calculator just as they appear. If you are doing them piece by piece, remember, exponents come before you multiply, so make sure you do 2 to the 5th first, and then multiply by 1, or whatever your numbers happen to be, but make sure you do the exponent first, or just follow my advice and just type the whole thing in at once. Once I do this, I realize that after 5 days, there's going to be 32 zombies. Not many, but remember, exponential growth starts out really slow and then continues to increase very quickly as time goes on. For the next part of this problem, they asked me about 15 days or 25 days. Well, all that's going to be changing then in my model is just going to be my exponent. Everything else is going to remain the same. So what I'd like you to do is pause the video and try to work those two out. Make sure you're getting the answers that I'm getting. So here are my two models and my two answers. Notice all I did was change the exponent. Everything else remained the same. So 15 days ended up with about 32,000 zombies. And after 25 days, I'm over 33 million zombies. So once again, we see that idea of exponential growth starting out really slow, but then continuing to increase very, very quickly as time goes on. Okay, take a look at this next part of the problem. In this case, I want to know how many days is it going to take until the zombies pretty much have wiped out everybody on Earth. So I'm using a population of about 7 billion people as our Earth's population today. So notice this question is a little bit different than what's above, because this time I don't know the time. So let's kind of start to write this out and see if we can come up with some ideas on how to solve this. So the number 7 billion has 9 zeros in it, so let's make sure I get all those down. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's what I want the answer to be. This time I'm going to set that equal to 1 times 2 to the, well, I don't really have any idea what that exponent's going to be, so I'm just going to put it to the x power. Now, we have a brand new kind of equation to solve. I don't know how to get an x out of an exponent. Or if you're watching this as a review video, at that point, maybe you do. Maybe you know about logarithms. But at this point in our lesson, we don't know how to get that x out of there. So instead, I really only have two options. I asked you guys in class what we could try, and many of you said, well, why don't you just guess and check, which at this point I think is a fantastic idea. It's one of the few options we have. So start plugging in some different values for x and see what's going to get you an answer of 7 billion. Now, we probably won't get 7 billion exactly. So all I would want would be a range, like between day 40 and day 41, or between day 55 and 56. I would just want the range of values from when we go under 7 billion to over 7 billion. So that would be one method. The other method that some people came up with was that we could graph it. And I thought that was an excellent idea. It's a way that we can get a much more accurate answer than just guess and check. If we were going to graph it, I'd say, and remember we've talked about this idea before too, I would enter one side of my equation as y1, y1, and enter the other side of the equation as y2. So tell you what, let's switch over to the calculator and take a look at each of those methods, the guess and check method and the graphing method, and see what answer we come up with.